Good afternoon, everyone. Welcome to our 10th and final installment of the USDA and WSSA webinar series. We're going to go ahead and let the room get filled again, and we'll hand it off to Dr. Culpepper in just a minute. So bear with us as we load the room. Good afternoon, everyone. Thank you for joining us again for the WSSA USDA webinar series. I'd like to introduce Dr. Stanley Culpepper, President of the WSSA, to start us off today.
Thank you so much, Eric, and thank each of you for joining us. It's been a wonderful 10 series webinar with the USDA and WSSA, and we have been just so pleased with your participation, and I wanted to thank you for that. As you know, if you've been here before, I'm going to turn it over to Dr. Young, but today, for just a minute or two, I want to take a second and give you an update on the WSSA calendar moving forward through the summer. For those of you who are WSSA members, or those of you who aren't, we'd love for you to join. But the WSSA symposiums for our 2023 meeting in Arlington, Virginia are due this Friday, June the 10th. So if you want to put in a symposium potential for that meeting and have not done so, please get that into Carol Mosley by June the 10th. Next Wednesday, Tuesday, June the 15th, 2 to 3:30 Eastern time, the WSSA is going to host the US EPA as they provide our members an overview of the pesticide re-registration process, and they're going to give us updates on DCPA, diuron, and flometron. Into October, in fact, October the 1st, the WSSA Innovative Grants Program, our very first, is due to our WSSA Finance Committee Chair, Greg Elmore. And also, our next symposium, hopefully it'll be as wonderful as this symposium has been, will be sometime in September or October. We haven't set the date yet, but it'll be the current regulatory and legal environment for weed control products. And that symposium is organized by Dr. Peter York. And then finally, sometime later in the year, our last symposium, which again was supposed to occur when we were in Vancouver, the North American Kochia Action Committee, Priorities for Coordinating Research, Communication, and Outreach, will occur. Now, with that said, again, I want to thank you so much for your continued participation, and it is my privilege to welcome you and to introduce Dr. Steve Young as your moderator. You already know this, but Steve is a weed scientist and the National Program Leader for Weeds and Invasive Pests at ARS. Steve, take it away.
Thank you, Stanley. Appreciate that. And like I said the whole time, WSSA has been really tremendous support for having this webinar series. And I also like to thank all of our speakers. We've had some really excellent talks, heard a lot of information on weeds, invasive plants, and really a great series to be part of. So hopefully most of you have been with us. If you haven't, again, I'll remind you to check out the website where we've got these recorded. Feel free to view those at your leisure. But I want to introduce today our last talk, and this is going to finish up our section on impacts. We've been talking, we started out with tools for control, then we talked about mechanisms, and now we're going to talk about the impacts of invasive plants and weeds. And to do that, we've got an individual here, Dr. Roger Sheley, who's with the USDA-ARS service. And Roger's been involved with ARS for years, working on this topic of invasive plants, ecology, trying to get this figured out. And Roger, I'm going to just ask you a little bit of background about how you got to your position there at Burns, Oregon. Just share with us a little bit about that before you launch into your presentation.
Well, sure. And thank you guys for having me here, and thank all of you for participating in this. And I'm guessing I know the majority of you since I've been around since the beginning of time, and have probably shaken most of your hands and at least visited, but I appreciate that. I got here, I was a professor at Montana State University for about 10 years. I was the extension noxious weed specialist for the entire state, which you can imagine is pretty daunting. I enjoyed it a lot and had a lot of students and enjoyed all of them. And I had an opportunity to come to Burns to work with the ARS as a lead scientist. And the reason I really did that is I grew up in Oregon, and I'm from Oregon, and Tony Svekar is a good friend of mine. And the opportunities that I saw there to make a huge impact on our field was greater than anything I'd ever seen. So I decided to go for it and have been here now for about 20 years and have enjoyed it all and still do.
Excellent. Yeah, thanks for that, Roger. Appreciate that. I think, like you said, you probably met most of the people in our audience, and I think today we're really going to be in for a treat here to hear about your work really over the last probably several decades on this topic of invasive plants. And I'm going to just go out on a limb here and say invasive annual grasses, but you can correct me on that one. But I'll turn it over to you, and yeah, look forward to hearing what you have to say.
All right, great. What I'm primarily going to talk about is really, I know he mentioned impacts. Impacts are related to all of this, but primarily I'm going to talk about restoring and why restoration is so critical for managing invasive plants, and how we might begin to change our thinking about restoration. And historically, majority of people have tried to take what we do in farming systems and convert them to rangelands. And usually it's the exact opposite thing that we should be doing as far as restoring and getting desired species established. And so I take a real ecological approach. What I also am trying to do is to show you what I found out about why restoration is so important, and then talk a little bit about how we might go about doing that in a very scientific sort of way, rather than try something and say that failed, or rather than keep trying different things and it works here and works there. What I've spent my career doing is to try to come up with some ecological frameworks and ecological ways of thinking about invasive species and invasive species management and restoration in a way that really does include the science behind it, which is, of course, the ecology aspects of it. So I try to use our ecology to help us figure out how to manage better. One of the things that I wanted to bring up was why restoration is critical. And if you look at the slide, it's on my left, and the slide on the right, what you can see is there are very complicated ecosystems. I love them. They have, if you look closely at them, they have early emerging perennial grasses. They have later emerging larger cespitous grasses. They have annual forbs. You can see some later perennial forbs, and even some sagebrush in these systems. And all of these plants are doing something in that system to make it sustainable. They're all cycling nutrients, cycling water, part of the energy flow of the entire system, and they're contributing to one another's ability to survive. And so when I talk about a community, these pictures sort of represent what I consider to be healthy, functioning plant communities that are doing all of the things that they're supposed to be doing and providing the goods and services to humans that they provide. When you think about these systems, we come out of winter in the West, most of these fields and most of these sites are, the soil moisture is at field capacity. And when it's at field capacity, as the season progresses, the soil moisture profile declines from top to bottom over time. And what you'll see is certain species will senesce while other species come in, and they take advantage of the moisture in the various soil profile over the years. And what we have is over time, over the entire season, we have something that occupies every space. Early emerging species like Sandberg's bluegrass will use the surface soil moisture, as will the annual grasses. In some cases, then as the soil moisture profile declines, the cesspitoe sponge grasses begin to use the moisture, and it declines further. The forbs begin to use the soil moisture. They're deep tap rooted. And then finally, late, even in September, we can find sagebrush still growing by accessing soil moisture very deep in the profile. The neat thing about these systems is that all of the niches are occupied. They're operating at their highest functional potential. All of the processes, the ecological processes, the biomass production, the entire system is completely filled. And this is a very difficult situation for invasive weeds to invade into. And as a management practice, we need to begin to start thinking of our goals in management as trying to, how do we best occupy the niches that are in the system? And I'll show you a little bit of research we did that sort of supports that notion. In this case, Dr. Carpinelli and I went out and we made about 200 or 300 different plots of desired species in all kinds of mixtures and combinations. And we did it in a way using addition series design that allowed us to assess the degree to which each plot had differing niche occupancy. And so 200, 300 plots, because we use addition series, which is a factorial arrangement of desired species densities. And then we went into each of those once they're established, and we added spotted knapweed to the top of them. And here's what we found out is that as you increase, because what the addition series allows us to do is to calculate the degree of niche occupation and the role that each of the species are playing. So what we found out is that if you have one species, you can see where the spotted knapweed's on the y-axis. We had lots of spotted knapweed. We had less spotted knapweed when we had 2 niches filled, and we had even less spotted knapweed when we had 3 niches filled. And so that was really intriguing to us. And we often talk about resistance and resilience on rangelands, and this is the mechanism that we can use to help us develop a certain degree of resistance by invasive plants. We did other studies that were sort of the reverse of building the communities. We took some communities apart. We went to those really nice communities. And I consider annual grass invasion phase 1 of a 2-phase process. Annual grasses will come in, they'll burn, they'll take everything out. And then what's happening is you're before the perennial forbs or the perennial grass or the perennial invasive weeds show up, you just have annual grasses, but there's a huge niche under the annual grasses that are just ripe for the invasion of the perennial weeds like spotted knapweed. So I see annual grasses as the first to invade, and then perennial weeds like spotted knapweed and diffuse knapweed as being able to reach deeper down into the soil. So we went into these really nice plant communities, and we took them apart functional group by functional group. And in the first case on the left, phase 1, we were working with Medusa head. In that system, we took the shrubs out, we took the annual forbs out all separately, took taprooted forbs out, took deep rhizomatous forbs out, and took perennial grasses out. We took the mosses out, and then we removed everything. And then there's one plot that was the control plot where we didn't remove anything. And what you can see here is that here's if we remove nothing. So we got some invasion for sure when we put Medusa head seeds on each of those plots. But what you can see here is the relative role of each of the functional groups in resistance. And of course, for annual grasses, what we found, the primary barrier to invasion is these perennial grasses. Primarily, as a matter of fact, sandbirds bluegrass, because they occupied a similar niche. There is other evidence in the literature that these annual forbs are important, but primarily we had the grasses being the primary defender of the site from invasion. Just a real quick side note: each of these functional groups had some role to play, and you would think that in this plot where everything is removed, that you would have the maximum amount of Medusa head. But what happened was this site was so barren and so hot, the abiotic factors, heat, and would not allow anything to establish. So I guess one way to develop weed resistance plant community is just bare the soil completely and keep it that way, because I think it's hard for Medusa head to get in. Well, I'm not recommending that. I'm just saying that that was an interesting thing. But by and large, for annual grasses, the perennial grasses were by far the most important component in resisting invasion. In phase 2 invasion, we went into a very healthy plant community, and we took nothing out. We took spike moss, shallow forbs, deep forbs, grasses, all forbs, and then we took out everything. And what you can see there is that those plots where everything was taken out, because this system is wetter and the abiotic conditions aren't as harsh as this system. We had maximum spotted knapweed in this case, invasion, where we took everything out, just like we expected. And then we also found that in these deep taprooted perennial weeds, the forbs collectively really were the biggest barrier to invasion. And so it makes sense that if you're going to do management and you're going to focus on trying to occupy niches, that you really focus on those species that have similar ecological traits as the weeds that you expect to invade. Of course, what we'd really like to have is the full complement of a healthy functioning plant community, but restoration is an iterative process where you usually are trying to get one portion of the system put back together. And then after you do that, you try to put more of the system back together and more of the system back together. And so what we know is it's easier to restore annual grass infested areas than areas where you have both annual grass and perennial weeds. And so these would be focus sites for you to begin to try to restore. But the bottom line, as far as I'm concerned, is that there are really two goals in invasive plant management. One is that we have to maximize productivity, and two, we have to maximize diversity, but we have to maximize functional diversity. And by that means we have to maximize niche occupation. If we can plug all the holes with something we like, it makes it very, very difficult for plants that we don't like to get in. And so most of my presentation is really talking about how we think about using science to help us maximize productivity and maximize functional diversity in these systems, which is the goal. If we're not going to do repeated control, we can't afford to do repeated control. And ecologically, we may have, other than money, we may have ecological concerns about just controlling the weeds every time, which would be about every couple of years. Then we're going to have to focus on restoration. Restoration is really expensive, and that's the problem. When we use farming system techniques, like just let's plow it and farm it, these aren't. It's very difficult to get these things established. If we use a no-till drill and we use crested wheatgrass, it costs this is old. It cost back then about $40 an acre, but we'd get a 50% chance of it being successful. And if we use natives, it would cost us about $100 per acre. but we'd only have about a 25% chance of being successful. And if we have natives with invasive species, there's really only a less than a 5% chance of getting a native stand established when you go through $150 worth of inputs. That makes restoration very complicated. And what we can see here pretty easily is that our farming system techniques really do not apply to rangelands. And you can think of it like this. Most of the crops that we're trying to grow came from some other country and are very analogous to the weeds that we have. And so if you take the same systems that we use to farm and you try to do that on our rangelands, you actually are going to get more weeds, not less. And so we have to rethink the whole process of how are we going to restore these rangelands. So we have a situation like this where it's completely dominated by annual grasses, and we ask ourselves the question of what are we going to do with it? One thing we could, I'm convinced that just by killing the weeds, we can do it temporarily for a couple of years or a year, but all that does is open the niches. And in order for us to be successful in invasive plant management, we have to treat the underlying cause of the problem. And that is that we've opened a bunch of niches. And if you think just nature abhors a vacuum, and what happens is these open systems are rapidly invaded by those species that have the growth rate traits to take advantage of all of the open niches. And we know what that is, stuff we don't like the annuals come right back. And so we have to start thinking about closing the niches if we're going to be successful. And I know we're all thinking about that now. I've talked like I talked about 20 years ago, so I know you're farther advanced than I'm recognizing. Thank you for that. But one of the things that I like to think about is how we can be more successful at restoring things. And I use this analogy that many of you have probably seen, where if you were an engineer and you wanted to build a bridge, one of the things you could do is collect all your tools together in a pile and take them down to the water. And then you could just sort of mentally imagine how it might work best and start tacking it together. The alternative would be for you to understand the principles and the concepts around engineering, which understanding the basic science, which is physics, and understand enough physics principles that you know that these angles are the strongest part of any design because of the bracing system. You know all the principles associated with how to make this bridge. You develop this very thoughtful and principle-based plan, and you give that plan to the construction crew, and they put it together the way you've planned it. And next thing you know, you have a bridge that's very sustainable. If you would have used the other bridge or the other method and just taken your stuff down there, you would have ended up with some kind of circus ride, carnival ride type something across the river that, well, I wouldn't walk on, you wouldn't walk on, or even let alone drive on. You might, I don't know, depending on who you are, you might let your wife or girlfriend try it, but that's your business. So what I want to do is say the basic premise about how we're going to restore systems really has to be upon understanding what causes the invasion and understanding what causes the plants to do well, and what causes weeds to, what's going on out there that causes the weeds to come in, and what can you do to affect the causes of the plants you want, is really the question that I like to deal with. And for one, we know these plant communities are always changing. The question becomes what's causing it, and how do we either impede it or how do we accelerate it? And that's the kind of thing that we're interested in weed management. I like to use this example of what a cause is, because a lot of people don't really feel comfortable with understanding what the cause of invasion is. And this is the simplest version of what I know about an invasive situation. Is on the left, you have what the Malheur Wildlife Refuge considers their primary objective. They're mandated to have massive amounts of water, and they want to have that water, as much water as they can get. And then the waterfowl attracts the waterfowl, they come in, and then they use the neighboring ground for the farmer's ground for getting feed and being off the water, and it works beautifully. And so in their laws, or in their mandates, they're forced to flood this with massive amounts of water. But over 40 or 50 years, the picture on the left shows you that this entire area has become invaded by cattails and tules. And so you say, that is just turning this entire refuge into a wreck, right? And that's the way they felt that sometimes. And so you're losing the ability to flood these areas because they're invaded with something that's taking advantage of the water and does well in that system. And if you're going to do something about that, we know what the cause is. The cause is if you flood this thing annually for 50 years, you're going to end up with cattails and tules. The solution isn't to go spray the cattails and tules, because that just simply won't work. You have to change the underlying reason. And so what they have to do is set their watering scheme up on a 5-year rotation plan, and they can put water out and dry it periodically, so that, and maybe dry it and spray it periodically, so that they can address the underlying cause of why they've got all these cattails and tules. And I give you this example just as a way to get a feel for what a cause might be. In this case, it's the continuous flooding changes the environment that makes it more conducive to something they don't want. And so by going at the beginning of the spring and turning on the spigot from the Steens Mountains and pouring it into that refuge, ultimately over time that turns it into something they don't want. So they have to be strategic about how they release their water, and that they let areas dry out, and they control some of the dry areas occasionally. And once they are on a system like that, then they can make it sustainable. In ecology, there's a way of looking at causes that I think is really the ecological basis for integrated weed management, which is that they say that there are basically three major causes of succession: site availability, that is how many niches are out there, and if a plant comes, does it have a way to get it? Does it have a niche? And then the species availability, which is that if the niche opens for a species you like, is that species available to fill the niche? You have to have both of those things happen in order for a plant community to change from something you don't like to something you do like. And then once the plant or the population arrives, what are all the things that affect it that cause it to do well? And it's a combination of these three things that really ultimately determine what causes a plant community to change from bad to good, or from good to bad. And so that hints to you the kind of the basic cause of why these plant communities are changing. And so let's just explore that just a tiny bit more and see if we can figure out how we might use that information to help us design restoration programs that are based upon these causes. In this case, it's a much more, what's interesting about this is that you can see the causes on the left there: site availability, species availability, and species performance, the same ones we just looked at. They cause the plant communities to change. Each one of those causes is influenced by different ecological processes. For example, site availability is affected by disturbance. That is, how many gopher holes create bare ground that open sites for things, that kind of disturbance. Also large scale disturbances, okay? And each of those are influenced by many factors that you can use to manage the disturbance: the size, severity, the time intervals, the patchiness of the disturbance, all influences, all those modifying factors influence the disturbance, which ultimately influences the cause. And all of that is true for species availability. The processes are dispersal and propagules. How many new species are around to take the spot that gets open, and how many weeds are around. And then species performance really includes a whole series of processes. And I think your favorite tool is probably hinted at, like there's some herbivory, natural enemies under the stress, but all of these processes are things that we can manage in invasive plant management to sway the plant community from something we don't like to something that we do like. And I always get more excited every time I look into this, because we talk about very few tools, but the truth is our toolbox, we've only ever looked at the upper layer of the toolbox. Our toolbox is full of all these things that we can do to influence the plant community and how it might change. And from a new researcher's perspective or a new manager's perspective, to me, that's exciting, because we haven't really hit the tip of the iceberg as far as all the things that we can do to deal with invasive species. And there's the whole understory storage of the toolbox that we haven't really even opened yet. We tested this and tested whether or not this actually works, this kind of idea, it makes sense. And we went into, this was up near Kalispell, Montana, not that far up, Polson. And we went into this system, and it was an interesting one because it was a series of potholes and rangelands with potholes of water in them. And we picked sites that had disturbance already in good shape. We picked another site that dealt with species or site availability. We found species that areas that were already had a nice remnant seed source of natives, and that addressed species availability. And then we went into a system that was more near the wetlands, which addressed species performance. And we decided what we would do to each of those. And this is like 500 plots, but we decided, and they're large. We decided what to do based on what the current condition looked like. And so if it was disturbed, we added seeds and we watered it because we already had a niche open. We just needed the species available and for them to do well. In the wetlands, we didn't have any disturbances, so we added those. And we also seeded, we also killed the weeds. And with where there's remnant species, we added some disturbance so that they could have a place to grow. And we also added some water to those. And I'd love to tell you it all worked out beautifully, but it didn't. 2 out of the 3 cases, it worked perfectly. Okay, so we predicted a wonderful outcome, 2 out of 3 cases. And this was huge. If you want to read this, it's worth a look. It's in Ecological Monographs in 2006, and it's worth a read, I think. It's a monograph because it's a big, thick study that included lots of things. But basically what we determined was you could be successful 2 out of 3 times using this system. And in most of what we do, we're successful not at all, or we kind of give some credit to it. So we say about 1 in 12 times you might have a successful restoration program, getting things established that you wanted. But using this system, then we were able to be successful 2 out of 3 times. And I don't know if you'll see the numbers, but here's the control. Here's how many invasive plants we had. You can see that we lowered them. Here's the number of desired species we got with each of the programs, desired grasses and desired forbs. And you can see we dramatically increased all of the native grasses and native forbs. It was interesting to me that seeding really made a big difference, even where we already had a remnant native stand that was supposed to supply the seeds. So I can't really explain that. And I didn't have a lot of luck with the herbicide application in that system either. So that's the one that went funky on us, and still trying to figure that out. But anyway, even if you use this system, you could be better off 2 out of, to get To get a stand established that you're interested 2 out of 3 times is pretty amazing. And that's what we think using this system will do for you. So we set this system up in a more formal manager user-friendly type of system, where you step one is you do an assessment. You try to figure out what of these 3 causes are actually most important in the driving of the plant community in the system you're in, and what are the associated ecological processes that need to be adjusted. And then step 3 on this is that we have made and spent the last 25 years or 30 years developing ecological principles, just like the engineer has physics principles. We've been developing ecological principles that really are the kind of principles that you can use to influence each of the processes that direct succession. And then we associated each of those principles with the actual technique you might use to make that happen. For example, an ecological principle might be, you need to have infrequent disturbances in these systems where you have native plants. And so when we're working with it, we'll do types of things like shallow seeding, shallow disking, shallow tilling, no-till drills. We don't like fires, so we reduce fuel loads in these systems. Those are the kind of things that you can do to favor desired species. Those are the tools and strategies, and they're based upon these ecological principles that we've developed using over 20 or 30 years of research. And then again, I said that this restoration is an ecological, an iterative process. So you come up with a plan, you try to do it, and then you go back and you watch it, and then you see where you are next, and then you redo the plan. Restoration is on rangelands is a never-ending iterative process that you always have to be involved in the management of the land. And this allows you a thoughtful framework on which to base what you're going to do, that's based on sound science, that's represented here by the ecological principles, and this framework that allows you to address the cause of the process that's influencing it, and address the cause of why you have weeds or why the system is or isn't going in a way that you like. Now, most people choke at this point and say, I don't know how to figure out whether site availability, species availability, or species performance is a cause of anything out here. I don't know how to do that. And then, and so what we did is put together, they have a system out there where there's about 13 or 17 different rangeland indicators for when you are assessing rangelands. You assess them using this rangeland assessment guides that was developed Pike and a bunch of other people. And what we did was take the rangeland assessment and convert it into something that you could use to determine whether or not or to the degree to which site availability, species availability, or species performance is the main driver in your systems, or the degree to which they are a driver. And then the model links it to the processes that are going on and has the principles associated with those processes. So you can actually use the rangeland health indicator system to determine the degree to which the 3 causes are actually operating in the system you're working in. And that just helps people be more comfortable that they're addressing the right causes, and helps them figure that out. Once you know the causes, then these causes are linked to these ecological processes, all of these, and then again, these are all the ecological principles that helps you decide what to do with disturbance. So instead of doing farm work, or instead of managing plants and trying to get the plants in, you're really managing the ecological processes that are responsible for driving the plant community one direction or another. And if you want to be sustainable and you want the thing to last for a long time, you're really going to have to address these ecological processes because they're fundamentally what's driving the change. So if you put another species out there and you luckily got it established, but you haven't affected the underlying cause of why that plant community is changing from something bad to something good, then it's not going to last for you. Okay, so you really need to think about how you're going to address some of the key primary driving ecological processes. And for annual grasses especially, we've put this entire system together with ecological principles that we know today. And ecologists are just like physicists. They're continuing to develop new principles, and ecologists are continuing to develop new ecological principles on which we can base land management, especially invasive species management around. So once again, you see the entire 5-step process. Once you know the ecological processes, then you can begin to decide what tools and strategies influence that process, which will influence that cause, which will help your plant community drive towards something you like. I get a little bit into the details just to show you how the thought process actually works. Is if your process you decide is disturbance, couple of the principles are, well, you don't want fire, and we know that favors invasive species and plants with rapid growth rate characteristics, and you want to create safe sites for the species you want, but you don't want to release a bunch of nutrients with massive disking or farming type, because if you let the nutrients go in that system, the plants with the fastest growth rates are going to get it, and that's going to be the weeds. So what you do, so the way this system works is you look at the process of disturbance, you see these two principles. There's many of these principles, but this is just for an example of how this thought process works. So what you would say I'm going to do is I'm going to shallow disc 3 times. And I mean, I'm just gonna disc an inch, and I'm gonna do that 3 times to try to see if I can create some safe sites. And then I'm also gonna manage the litter in this system so that it won't burn. And I might even plant something in there that is late maturing and stays green later into the year, so that there's something that can have some moisture in it that will help the fires, to keep the fires from burning through the system. I might, in my seeding mix, add a little bit of forage kochia, and that will stay green in these systems later in the year. So when I plant my seed mix, I'm going to add some forage kochia to it. So that's how you use this to think about things. And when it's all said and done, it looks kind of like this. I have the initial plant community and the final plant community. I have site availability, species availability, and species performance. And to address site availability, well, we know what we decided for that. We're going to disc it 3 times very shallowly and add maybe some kochia in our seed mix to minimize, to plug that late season thing that causes fires, to minimize the fires. So we're going to add some kochia to do that. Species availability, we went through the same thought process for that. And species performance, we went through the same thought process for that. And this puts together our management plan. So now we have a management plan. You can see, well, we're hot on seeding Sandberg's bluegrass, maybe some 6-week fescues, maybe even some annuals, forbs. And that way they're occupying the niche we want to occupy. We tossed a little cereal rye in there because the cereal rye also occupies the niche and takes up some of the nutrients that we released really fast and then goes away because it's an ephemeral annual. So you can see what we thought of here are the things that we could do to address to address the principles that are outlined. All of these come from principles that were outlined in our system. So then now you have a model, and then you can go out and test that model and see how well you like it and see whether it actually does what you thought it would do. And then you go through the process again, and that process will help you then redo your program and redo your plan for the next 5 years, and you'll know where you're headed again. When we've done this stuff, what we have found out is that in normal management of rangelands where we're trying to restore it, we're successful maybe 1 in 12 times. But if we use this ecological approach, we are actually successful 2 out of 3 times. And the longevity of the system is much, much more sustainable because we've addressed the underlying causes of the problem. We've changed the ecological processes that were influencing the causes that allowed the weeds to come in, and we've changed those processes to be in favor of desired native plant communities. So hopefully for you, that's an example of how you might use science and ecology to help you figure out how to develop management plans that are sustainable and successful, and that when you use the principles of ecology to help you put together a management plan, it's like that bridge that's going to be much, much more likely to be sustainable and hold the weight you want to do. These systems last much, much longer. You always have to rethink what you're doing because, again, it's an iterative process. And so I just got a few minutes left, but what I wanted to do is let you know that we are also working on a similar kind of concept, but we're trying to quantify it. The system that I just showed you is more difficult to quantify. We are using a mathematical system and developing a mathematical system for doing something quite similar. And this is based on the life history of species. Life history is just that you sow some seeds and the seeds germinate, they emerge, then they become established and grow to be juveniles and then adults. Well, that's awesome. And each one of those transitions, so it's a states and transition thing, each one of the transitions, like in this model, for example, G stands for germination. So we put seeds in the soil, they germinate. Each one of those transitions is associated with various important processes. And these processes are related to the things that either impede the establishment of the species you want or help the species you want. And so you can take a look at these processes and figure out how to begin to manipulate them. This is a mathematical formula, by the way. This times this equals this, 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 blah, okay? And so what's really cool about this is that you can conduct things like sensitivity analysis on these models and figure out where we're having problems getting things established and getting our system to go. And we just published, just 10 years ago, published the papers that show that this EM is a critical portion of the process. What we're trying to do now and what I'm trying to get across now is that as scientists, we're really moving to quantify our ecology, and this system allows us to begin to use math to help us determine what to do. And the other one that I showed you is really based on the principles and just applying some of the principles. And I think it's for now, it's easier to use the first one, but in some time, I think you'll be able to use this. And the cool thing is that you have a model like this for each of the species. And when you spin this model for multiple years, you can see the outcome of your management. As you change each of these processes at each one of these transitions, the community changes. And I think someday we'll be able to use this system combined with some of the GIS technology that we have to make landscape scale mathematically based management decisions. We're just not there yet. And I think with that, all of this stuff is about adaptive management. And the only thing I'd like to do is encourage those of you who are engaging in these types of things to consider always creating a control in your and replication in your management, so that you have a way to determine whether or not the things that you did are what made the plant community to change, or whether nature did it on its own and you were looking good because of it. So I think adaptive management has to have controls and replication so that we can really narrow down what it is we've done and whether it worked or not. And I would encourage you guys to put 5 or 10 of them out there across the landscape, just areas that you didn't do what you did to everything else. And that will help you in the future become better stewards of the land. Anyway, that's my version of how we use ecology to better manage invasive plants and how we restore these systems. And I hope it made some sense to you, and hope something there clicked for you for sure. Thank you all.
Yeah, thanks, Roger. That was great. Really comprehensive, and a lot of the underlying principles I really connected with. And I know probably a lot of our audience members are probably thinking of that right now. But before we get into a couple of questions, I just wanted to, I really like your bridge analogy with the picture you showed, and thinking about the principles and how they kind of lead to a solid bridge that we know is going to actually do what it's designed to do. And I guess one of the things is, as you look at a bridge, and I don't want to get too kind of detail here, but there's obviously the major structural aspects of a bridge, and then there's the minor kinds of things. And I don't know if you could like help us visualize, like, what are the major kinds of things? Like, is it, and you started with your presentation on a full soil profile of water, so the profile is filled up with water. I mean, is that one of the major towers that kind of supports the roadway per se? And I don't know if that makes a lot, but I'm trying to kind of visualize what you're mentioning in your talk. And I don't know if you can do that, but I just thought I'd throw that out there.
Well, for me, the primary thing that we have to understand is that some of the functional groups are critical in keeping weeds from coming in. And the data that I showed, were one of them was hinting that increasing functional diversity was important, but the other one actually showed that there are different functional groups for different species that are invading, and that getting those established is, without a doubt, in my view, the only way we can deal with weeds effectively. We have to fill those niches with the species that occupy the same niche as the invader, so that when they get there, they don't have any place to grow. And to me, that's a fundamental thing we're working towards when we're talking about invasive plant management.
Yeah, and I agree with you. And the one thing that I think about is, in your model and some of the things you've shown, I think of how invasive species have actually taken advantage, or actually have done what you're showing, in their own abilities. We talk about establishing the plants we want, but at the same time, those that we don't want have actually done all of the things that you've kind of outlined. They're high seed producers. They're finding the niches. They're taking advantage of soil moisture. They're extending, life cycle into the season. So all those things, you look at the weeds, the invasive plants, and like, hey, there's our model. Let's mimic it with what you've done and what you've shown here. I think that's really an important part.
After spending 45 years studying invasive weeds, I don't hate them anymore. I spend a lot of time hating them. But when you learn so much about something that is has evolved such an incredible life cycle, and so many traits and so many different strategies, and they're just amazing, there's no way you can hate them anymore, because they're just a complete world of amazement if you start picking them apart as to their strategies and the things that they do and their traits. Incredible plants, absolutely, staggeringly incredible.
Yeah, and speaking of the plants, we've got a question in the chat box. You mentioned kochia, and we know that there's an invasive kochia, but just can you clarify? You're talking about forage kochia, right?
Yeah, forage kochia. And what I want people to know is that, so I expect that if you have annual grasses and you don't like fires, the one single way I know to deal with it, well, I guess there's two. I mean, I think reducing fuel loads is really valuable, but from a community ecologist standpoint, that system is missing deep taprooted late summer species. And so the one way for you to try to interrupt the fires is to try to establish something that that grows later into the season and get them growing so that when the lightning strikes, the system's got a little moisture in it, some green stuff, and it doesn't burn as much. And that's what I think happens in the native systems. What I just said, forage kochia, yeah, and kochia has shown to stay green later. If you want to stop the fires, you need to plug some late maturing plants in them. Certainly if you plugged in something like yellow star thistle or spotted knapweed, I think you'd have a lot less fires, but I don't think you'd be very happy about it. But finding something that you like, nature's going to put spotted knapweed and yellow star thistle into them if you don't get something you like established in those niches.
Yeah. And I know there's a lot of work that's going on finding those more desirable species, within ARS as well. There's a question here on just your EBIPM. That is currently still available, right? Is that, if someone wants the information you're sharing, that's available at the?
Yeah. All of I have this put together well, it doesn't have the restoration. Well, it's all restoration. Anything you do out there is, in my view, if it's weed management, it has to be restoration. And because you have to plug the niches, and all of this stuff is available in the literature for sure. If you just type EBIPM, there I have for each of the stages, the 5 processes, I have a workbook that helps you figure out how to do each of those processes in a successful way. So
Yeah,
it's all out there.
And I would say, again, just a reminder for folks, contact myself or Roger. We'd be happy to connect you. I've got a question here about nitrogen deposition caused by smog and other forms of air pollution in terms of adaptive management. Any thoughts on that?
Well, I mean, the literature is pretty solid on that one. I mean, we know that there are examples, especially in California, in the serpentines, that, the industry's nitrogen has increased the nitrogen levels to the point at which invasion is much of annual grasses is much more readily. So yeah, we're pretty clear on that. It's not really that's not really even in doubt.
Yeah. And then we've got a question on, someone wants to know, as far as using adaptive grazing, does that address does that get us to the desired results that we're kind of after? And I realize that's, we're not trying to pick one thing out, because this is a integrated approach, but
right.
How does that kind of fit within this system?
Yes. So in addition, I don't know if you can still see my screen or not.
Yes, we can.
I moved it to something we call green and brown. And what this is, so grazing ends up being one of the tools that we'll have, that you'll find in things that you can do to influence processes, and grazing is certainly one of them. And in my view, grazing is likely to be, even with cattle, but a multiple group of species, and depending upon the timing, the frequency, and the duration, the intensity of grazing, I can sway a plant community with different types of animals in any direction you want it to go. So I think grazing is in itself a huge area that will likely foster the most value. In this system is trying to, this green and brown is really a simple system that we made for grazing annual grasses. And in this case, we basically just graze it when the native plants or even crested are brown and dormant. But the cheatgrass, is a fall emerging winter annual, merges in the spring too, but it'll stay green during times when the native plants or the desired cespitose bunch grasses are brown. And we advocate grazing anytime that the plants are, the cheatgrass is green. The animals will select right for it. They'll hardly even touch the perennial grasses. It's okay if they do. And And then we try to point in this green and brown system, and there's a how-to manual for this too, but we try to point to when you really don't want the animals to graze. You don't want them to graze when the cespitous bunch grasses just start to become green, because then they'll start taking that early leaf material out of the system, and you don't want that. So yeah, you can look at the green and brown. I'm convinced the proper kind of grazing, the timing, intensity, and frequency and species really can, I called it designer grazing systems. I can sway a plant community in any direction you want it to go with altering those combination of things.
Yeah, and I know that you guys are working on grazing right there at Burns, and I know other ARS units are actually focusing on that. So that'll be, you know, important information, especially as we talk about wildfires and, you know, the impact of invasive annual grasses on that. So
I should let people know that. Well, this may not be. I'm sorry if this is not right. SRM. I'm the editor of Rangeland Ecology and Management, and we're just now coming out with a special issue on grazing and cheatgrass, especially for reducing the fuel load.
oh, excellent. So that's actually a good segue into the end of our series. And I want to let everyone know that we're actually developing a weed science newsletter with ARS. And I'm going to share articles, research that's happening within ARS over the next, you know, months and even longer. And so those are the kinds of things that you'll find. I'd encourage folks to contact me to get on that mailing list. But anyway, I want to thank Roger for your presentation today. Really a lot of, you know, valuable information that folks can use, and would encourage people to reach out to Roger or myself if you want to, you know, want to get more information. But anyway, that wraps up our webinar series. Thanks again, everyone, for your attention. And thank you again to Roger and our other speakers for your outstanding research. And we'll look forward to seeing that as we go. So thanks again, everyone. Again, check out our website for the recordings, but we'll see you around. All right.
Thanks, guys.